So as we introduce Faraday's law represents that there is an induced voltage in a loop if we can change the magnetic flux in the loop. This negative sign is technically Lenz's law. It tells us that any current induced in a loop of wire will flow in a direction to oppose the change in flux. So in one of the example videos I posted for you, there was a loop of wire, and then there was a bar magnet that we would bring closer or farther from the loop. So let's talk about this for just a second. So our loop, let's say we're bringing this magnet. I'm going to start with it farther away, and I'm going to just draw it bigger so we can see it better. Though I suppose that wasn't that much bigger. But I'm going to move this magnet to the right and get closer to the loop. Now I know the magnetic field comes out of north and loops around and goes into south. So if I was to represent the magnetic field of this bar magnet in the region near the loop, the magnetic field strength would not be super strong yet because we're still a little ways away, or a fairly decent distance between the bar magnet and the loop. Now the loop, let me see, let's say we're looking at it from the edge. So the bar magnet's coming this way. We're looking at it from an edge. I don't know if I can draw this super well. Let's try though. So our magnetic field, our loop that we're putting this into is oriented. So the magnetic field lines that are passing through, at the moment I'm only seeing 2 of those that I've drawn passing through that loop of wire. So this is my loop of wire here. As I move my magnet to the right, I can draw all these magnetic field lines again, but now I'm closer to the loop. Let me draw that one better. So my loop is still here, but since the magnet is closer, if I look at my loop from the side, I now have, from my drawing, 4 magnetic field lines passing through. So we've gone from the first situation, the moment in time where out of my drawing I only have 2 magnetic field lines passing through, to a second moment in time when I have 4 magnetic lines passing through. So what we're seeing here is the magnetic flux through this loop increased between moment 1 and moment 2. So this just represents me bringing this bar magnet closer to the loop. Because this flux increased, we have more magnetic field lines passing through. That's why we know the flux increased. Because the flux increased, the loop itself is going to have induced current to oppose this increase. That's what Lenz's law is saying. So ultimately, we can think of this as our loop creating its own magnetic field. We would call this an induced magnetic field. It's creating it in the opposite direction of the magnet's magnetic field to try to get back to moment one, to get back to the flux that we had at moment one. So what we're seeing is that the induced magnetic field created by the induced current is opposite the magnet's magnetic field because it's trying to decrease the flux back down to what it was. In moment one, or at moment one. That's what we mean by the opposition. If the flux is increasing, then there's going to be an induced current in a direction to try to decrease it back down. So the magnetic field is induced in the opposite direction of the magnet's magnetic field to try to get back to two field lines passing through the area. Once we know that, we have to figure out what direction that means. So I put, because the current is going to be circling, I'm going to let my thumb be the direction of B induced. So in this case, I want this to point to the left. So if I take my right hand and point it to my left, my fingertips represent the direction of the induced current in the loop. So with my thumb pointing to the left, my fingers of my right hand curve away from me. What that means is in our loop, I apologize. I have some challenges when it comes to artistry. In our loop, our fingertips are pointing away from us up here. That means the current induced in this loop is flowing away from us on the top of the loop. If we twisted our wrist all the way around so that our thumb was still pointing to the left, let's see if I can even draw this. Our fingertips, oh dear, okay, I don't think I can draw that. Just rotate your wrist this way so that you have your thumb still to the left, but your fingertips are below your thumb. If your fingertips are below your thumb, they're pointing towards you. So the current induced would be coming towards us at the bottom, away from us at the top. So if we were looking at the loop from the left, from the left side, we would see I induced flows counterclockwise. Anytime we know that the magnetic flux is getting bigger and bigger because the field is getting bigger and bigger, the induced magnetic field will be in an opposite direction. For example, let me make a new picture. Let's say we have this same bar magnet, but let's orient it the other way. In this region, we know magnetic field lines point towards south. If I draw in my loop again, we're going from magnetic fields pointing to the left. If I move my magnet closer to the loop, so same magnet, but now we're closer to the loop, there's more field lines pointing to the left. This means the magnetic flux through the loop is increasing from moment 1 up here to moment 2. If the magnetic flux is increasing, there will be an induced magnetic field that is opposite the magnet's magnetic field to try to decrease that flux back down. So to be opposite the magnet's magnetic field, in this case, that would have to point to the right in the loop. So B induced points to the right this time. Right-hand rule, point thumb to the right because that's the direction of B induced. If I am holding my thumb to the right and let my fingertips curl, my fingertips curl towards me above my thumb. Above my thumb. That means in my loop, this induced current is coming up at me above my thumb, which means it would also go the opposite direction on the bottom. So if we looked from the left, in this case, so if we were standing over here looking at this loop, we would see the induced current flowing clockwise in this case. Lenz's law takes multiple steps to use. There's not always one clockwise versus clockwise and counterclockwise answer. So you can't memorize that part because that doesn't always stick or apply. So number 1, if you want to figure out the direction of induced current, you need to ask yourself, is the magnetic flux changing? Now, specifically through whatever loop we're talking about, Is that magnetic flux changing? If the answer is no, then there is no induced current. If the answer is yes, then we have to ask ourselves another question. Is the flux increasing or decreasing? The two examples we've looked at so far have both been situations where the flux was increasing. If the flux is, oops, sorry, go away, please. If the flux is increasing, the loop creates a magnetic field, so an induced magnetic field opposite in direction the external field. And what I mean by that, in the examples we just looked at, the external field was created by a bar magnet. That external field could be created by something else. It's just the field that exists in that region because of something else. Some other wire carrying current, some bar magnet. That's what we mean by the external magnetic field. So the loop creates an induced field opposite in direction to the external field if the flux is increasing. If the flux is decreasing, the loop creates an induced magnetic field in the same direction as the external B. And that's because it's trying to add those field lines back in to increase the flux back up. Regardless of which case, step 3 of this problem is to use the right-hand rule to determine the direction of current induced to create the needed B induced. So anytime you're looking at induction, inducing these currents, make sure you just slow yourself down and go through the thought process. There's no quick answer to answer these directions. To solve mathematically for a value of induced current, we use Faraday's law, which we did in a couple examples prior to this. But this, finding direction, slow down, think through those 3 processes or 3 steps of solving the problem. I'll go through some examples in the next video for extra practice.